In today's lesson, we are going to be looking at trigonometry problems in two dimensions. And the reason we specify two dimensions is because in the next lesson, we are going to be looking at trig in three dimensions. Now, two-dimensional problems are what you have looked at before. It's what you would have looked at in grade 10 with kind of application questions or scenario questions. Same thing here. We're just going to kind of basically be doing a little bit of a review of those concepts. Right. So with our 2D problems, right, we have to think about what ratios or what laws are we using. Right. So just as a little bit of review, a little bit of a flow chart that you can kind of go through. Right. So first, is the triangle right angled? If no, right, then do we know a side and its opposite angle? If yes, we use the sine rule. If no, we use the cosine rule. And we'll talk about other scenarios about when we use sine or cosine law or a rule, however you know it, or whatever you know it as. So there are going to be some other scenarios or characteristics that we're looking for to use those two rules. If it is right angled, right, that makes it a little bit easier because that tells us we are going to be using probably our tan or our trig ratios, our primary trig ratios, sine, cos, and tan, right? If it is a right angled triangle and it does not involve angles, then we can use Pythagorean theorem, or you might know it as sum of squares. So just a little bit of a flow chart to kind of help you think about what rules or ratios do we have to use. Right, I'm not going to go over the primary trig ratios. We've already looked at those with some of the other previous examples or in the previous lessons. But sine law. So sine law is a ratio of a side and its complementary angle, or a side and its paired angle in triangles. And it's saying that the ratio of the side and the sine of its angle is going to be equal to or equal among all three sides. Right? So here we have A over sine A equals B over sine B equals C over sine C. Now these lowercase letters on top, these represent the side lengths. And these capital letters on the bottom represent the angles. So a side and the sine of its complementary angle. Right. And this is used when two sides and an opposite side are known, or two angles and one side are known. So some scenarios we can kind of see here. Right. If I look at triangle PQR, I can use the information here to find out what this missing angle R is. And that's because I have a pair and a half pair. So that's what I like to refer to it as. Do I have a full pair and half a pair? In this case, I do. I have angle Q and side Q. This would be lowercase q. And I have side R, but I don't have angle R. Right, so that's what I refer to as a full pair and a half a pair. That's what I'm referring to as. We can also look at the scenarios, right? We do have two sides and an opposite angle, right? So I do have two sides and the opposite angle for one of those sides is known. If I look at the other triangle, BAC, right? I have, again, two angles and one side. I have side B, and I could think of, again, full pair and a half pair. So here's a half pair between angle C and side C. And I do have a full pair, even though the 150, right, we're more angle of 35 and side of 7. And the reason we say two sides or two angles in one side, and we don't really specify which one, is because if I didn't have this side length here, right, maybe I had this side length and this one was covered up. I can find this third angle because all angles in a triangle have to add up to 80 or 180. So even if I didn't have side B and I had side A, right, I could find angle A. I have a full pair and a half pair, or a second half pair here. So again, that's why we say just two angles in one side, because using those two angles, we can find the third one if necessary. Right, but I like to think of it also as a full pair plus a half pair. The other law is cosine law, and there's two kind of versions of it. It's the same formula, and it's just rearranged. And so sometimes it's a little bit easier to deal with the two already rearranged before plugging, rather than plugging things in and rearranging it then. So the first one is when we're trying to find a side length. And the formulas are all the same. If we look at these, they're all the same, and just we have our sides switched around depending on what information or what side we're looking for. Right? And this is used when we have two sides and a contained angle are known. So what we have an example here. This diagram represents two sides and a contained angle. Right? This angle C, is between these two sides. Now you can also refer to it as, sometimes SAS, or a sandwiched angle. Right? And if we think of it, because we have a side, then an angle, then a side. So we have a sandwiched angle. That angle is sandwiched between two sides. So I could use this information to help me find side C. So I'd be using this formula, right? Because I'm looking for side C. I have side A and B, right? So little a, little b, and I'm given the angle C. Right? So again, it's the same formula, right? If these sides were relabeled differently, if this was C, this was A, this would B, right? It's the same formula essentially, just again the labels are different. So again, you could just know one, and as long as you know one and just recognize that you have to maybe change around the letters based on what you have, or even just relabel the triangle so that it fits the formula or the law. The second version of it is when we want to find angles. So when we want to find angles, we use a slightly different formula. So cosine A equals B squared plus C squared minus A squared over 2BC. Right, and again, three different versions depending on what angle you're looking for. And this is used when all three sides are known, right? Or SSS. You have all three sides. Right? So when you have all three sides and no angles, you have to use cosine law to find one of your missing angles. Again, based on the triangle here that we have, angle C, or triangle ABC, we have all three sides. So we could find any one of these angles depending on which formula we use and how we arrange the sides. I find it easier when determining between sine and cosine law. Look for cosine law first, because it's only these two scenarios: the sandwiched angle or all three sides. Right? A little bit easier, or a little bit simpler in terms of figuring out what you have to do, because it's very specific. Right? Whereas the other ones, it could be a little bit more work in determining whether we can use sine law or not. Here it's two specific scenarios that we look for: either the sandwiched angle or all three sides. And if that doesn't work, then it's probably sine law. So let's go into some of these questions, just get practice using some of these ratios and laws. So Chester needs a new rope for his grappling gun, but is unsure of the length required to reach his favorite tree. He measures a distance of 15 meters away from the base of the tree that he wants to go up. From this point, the angle of elevation to the top of the tree is 72 degrees. What length of rope does Chester need to scale the tree to the nearest whole meter? So let's draw this out, right? So Chester has this tree. So I'm just going to draw a quick tree here. Oops. Maybe not the best tree. I don't want to spend too much time on it. So there's his tree. He wants to climb this tree or use his grappling gun to get to this tree. He measures a distance 15 meters away. So he measures a distance 15 meters away. And he notices an angle of elevation to the top of the tree to be 72 degrees. he wants to figure out, okay, what is the length of the rope needed to scale that tree, or basically what is the height, right, for his little grappling gun. So we can assume that the tree and the ground form a 90-degree angle. Right, so because this is a 90-degree angle, we are going to be using one of our primary trig ratios. So I have my reference angle here, 72 degrees. I have, or the 15 represents the adjacent, h represents the opposite, and I have the hypotenuse here as well. So what two sides am I dealing with? Well, I'm dealing with O and A. So if I think back to SOHCAHTOA, that tells me that I'm going to be using tan. So tan theta equals opposite over adjacent. Tan of 72 degrees is equal to the opposite, which is h over 15, which is my adjacent. To solve for h, I'm going to bring the 15 up to the other side and multiply. So 15 tan 72, or 15 times tan 72, is going to equal h. And we get, rounding it to the nearest whole meter, we get 62 meters equals h. So therefore, Chester needs 46 meters of rope. So again, just an example of using our primary trig ratios to help us find a missing side length. Example 2, Mr. Liu, Mr. Bond, and Mr. Marquis are doing CrossFit in the soccer field. Right? Liu and Bond are 23 meters apart. From Liu's point of view, the other two are separated by 72 degrees. From Marquis' point of view, the others are separated by an angle of 50 degrees. First thing we want to do is sketch a diagram. So for these two-dimensional problems, it's probably going to be, you might have to sketch the diagram to kind of get an idea of what the triangle looks like. Right, so we have three teachers that are separated. Liu and Bond are 23 meters apart. So let's start with that. So we're just going to draw a line 23 meters. Right, and we're going to say Liu and Bond are 23 meters apart. We know Marquis is going to be somewhere. We'll say he's up over here. The triangle might be not drawn to scale. That's okay, as long as you recognize that. Right, so Marquis is going to be somewhere over there. Right, so my point of view, the other two are separated by 72 degrees. So I'm assuming, from my point of view, they're separated by 72 degrees. And then from Marquis' point of view, they are going to be separated, or the others are separated by an angle. Oops, sorry, no, my mistake. So if I'm viewing it, I see them separated as 72 degrees. Marquis sees them separated as 55 degrees. Right? So again, it's from his point of view, how far apart they are. So if I look at one and then scan over to the other, what's the angle between those two kind of points of view? I see it as 72. Marquis sees it at 55. And me and Bond are 23 meters apart. So here is my triangle. And we want to figure out how far apart are Liu and Marquis. So we are looking for little b in this case, or this side. So looking at this, right, it's not a right angle triangle. If I needed to, I could figure out this third side, 180 minus 55 minus 72. And again, that missing side is 53 degrees. So I could find that extra information if I wanted to. I can clearly see that it is not a right angle triangle, so I cannot use my primary trig ratios. So I have to use something different. I can look to see if we have a sandwiched angle. and I don't have two angles, or sorry, two side lengths, so it can't be a sandwiched angle. I don't have all three sides, so it can't be SSS, so I can't use cosine law. So I have to use sine law. So because I'm trying to figure out how far apart Lou and Marquis are, I do want to find that side. So that is going to be at least one of my pairs. Right? The angle of 53 and the unknown side B. I do have another pair here of the angle of 55 and the side of 23. So there's enough information there to come up with, or to use the sine law to help me find side B. So here we're going to have side M, or little m, over sine big M equals little b over sine big B. So little m is going to be 23 over sine m, so sine of 55, equals little b, which is unknown, over sine of 53. With sine law, the first thing we're going to do is cross multiply. Let's get rid of these fractions. So we're left with 23 sine 53 equals b times sine 55. I'm going to get b by itself by moving the sine 55 over, and it becomes division. So 23 times sine 53 divided by sine 55 equals b. This just becomes one calculation. So 23 times sine 53 divided by sine 55. I get 22.42 meters equals b. Therefore, Lou and Marquis are 22.42 meters apart. So that's an example of using the sine law. Next example, a drive belt wraps around 3 pulleys as shown. Find the perimeter of the drive belt to the nearest tenth of a centimeter. So if I want the perimeter, I want the distance around. I'm going to assume that there's the rounded portion around each pulley is kind of negligible, right? That little rounded part doesn't really add much. We can assume it goes straight to and then straight over. So that means I'm just missing this unknown side here. We don't know if it's a right angle triangle or not. We can assume that it's not because it's not indicated anywhere that either of these other two sides are right angles. So we have to assume either sine law or cosine law. I'm going to start by looking at cosine law first. I am looking for a missing side, so do I have a sandwiched angle? And in this case, I do. Side, angle, side. So I have a sandwiched angle here. For reference, let's just call it A, B, and C, just so that helps me kind of come up with the measurements or the labels for our formula. Right, so we are going to use cosine law. We're looking for side A or X, right, or unknown, whatever you want to call it. So our formula is going to be A squared equals B squared plus C squared minus 2BC times cosine A. So A squared is equal to B squared, which is 16. So 16 plus C squared, which is 14.5, minus 2 times 16 times 14.5 times cosine of 35 degrees. Everything works out to, it's a one calculation, so we get A squared is equal to 86.16345. Right? I'd try to keep as many decimal places as possible just to avoid any rounding errors. But if you rounded this to like 86.16, that's fine as well. To get A by itself, I need to square root 86.16345. When I square root that, I get my A value, which is 9.3 centimeters. keep in mind, we want to find the perimeter. So we still have to go through and add up all of these side lengths. So the perimeter is equal to 16 plus 14.5 plus 9.3. And we get 39.8 centimeters. Therefore, the perimeter is 39 point, oops, not meters there, 39.8 centimeters. Our last example is a little bit more straightforward. It just says find the measure of angle G. So I'm looking for this side here. Right? Again, I don't know if it's a right angle triangle or not. I'm going to assume it's not because it's not labeled, it's not indicated. So that means it's either sine or cosine law. By looking at it, because I have no angles, chances are it's not going to be sine law. But I am going to double check for cosine law. I do have side, side, side. So it does have to be cosine law, because that is the only formula that I can use when I have all three sides. So in this case, we are going to be looking for cosine of G. Right? So we might have to relabel this, right? So depending on how comfortable you are with labeling the formulas based on the points that we're using or the labels of the points, you can use this using G, F, and H. If you don't like doing that, or it's a little bit too confusing, just relabel these points. Call this A, call this B, call this C. Right? It doesn't really change anything we're doing, right? It's just as long as you know if we're solving for angle A, because I rewrote it as A, then just make sure A represents G. Right? So again, different ways you can go about it. So I'm just going to rewrite this using the variables that we have. So cosine G, or angle G, is equal to f squared plus h squared minus f squared plus h squared minus g squared divided by 2fh. Cosine of G is equal to f is the side of opposite angle f, so 5.1 squared, plus h, which is opposite angle h, or 6.2 squared, minus g squared, which is opposite angle g, or 4.8 squared, divided by 2 times 5.1 times 6.2. Cosine G, this all becomes one calculation. Cosine G is 0.6548. And then I have to do the inverse. Bring the cosine over. Inverse of cosine of 0.6548. And G is equal to 49.1 degrees. So therefore, angle G is 49.1 degrees. All right, so this one is a little bit more... So this is a little bit just more of a straightforward question using the formulas, but again, it gives you some practice of finding an angle using the cosine law. Right, so in all of these, example 4. Right, so these are just examples of 2D trig problems, right? Just getting comfortable using our trig ratios or sine or cosine law to help us find missing measurements. Again, it should be reviewed from grade 10 because this is you would have looked at these types of problems. And this is going to be helpful for your next lesson when we start to apply these measures to three-dimensional problems. Right? So you do need to make sure you know these formulas for the three-dimensional problems.